In this video, we're going to look at the other source of random noise we'll consider in our receivers, quantization noise. Our motivation for doing this is the observation that noise figure paints a disturbing picture of amplifiers. Since noise figure is always going to be greater than 0 dB, which is the same thing as saying noise factor is always greater than 1, each amplifier we go through reduces our signal-to-noise ratio. Why should we use amplifiers if they make our signal quality worse? And just to make this concrete, in this example, we have very low noise amplifiers. They've got a noise figure of 1 dB, but we still cut our SNR in half at our output relative to our input. Our output signal-noise ratio is 3 dB lower than our input signal-noise ratio. This signal overlooks that our signal has been made much larger by this receive chain, which is important when we're comparing our signal against the resolution of an analog-to-digital conversion. Analog-to-digital converters have a minimum signal that they can resolve, called a least significant bit, or LSB, and that LSB can introduce significant noise into our signals. We need to take a closer look at the operation of analog-to-digital converters to understand why the LSB is such a big deal. Quick aside, analog-to-digital converter is often abbreviated ADC, and I'm going to be using that abbreviation. I've drawn a transfer function for an ADC on this slide. The x-axis is the input voltage, and it has units of volts. The y-axis represents a digital number that the ADC produces, and it's referred to as a code. So for an input voltage of 0 volts, the ADC produces the digital code 000, which represents the number 0 in binary. If the input is at the full-scale voltage VFS, the ADC will produce the code 111, which represents the number 7 in binary. Because the codes are discrete values, while the input is a continuous value, the transfer function has to include cut points where the output jumps from one code to the next, and these are called code transitions. That leads to the stair-step shape of the transfer function. The width of each stair-step is called one least significant bit, or LSB, because the code changes by 1 each time your input voltage changes by LSB volts. That stair-step is trying to approximate a straight line that would let the output codes linearly represent the input voltage. At some voltages, the output stair-step does that well. The voltage you get by multiplying VFS by the ratio of this code to the max code is exactly the same as the input voltage for this input voltage at right that spot. However, other input voltages pose a problem. The input voltage is going to be assigned to the 100 code for this input, but the input isn't at the sweet spot on the stair-step, where the stairs line up exactly with the linear approximation. So that means the conversion has introduced some error when it measured this input voltage. We tend to capture this behavior in signal processing or control models by imagining that ADCs look like transfer functions of 1, which assumes that they achieve their perfect stair-step approximation and convert a continuous V in volts to digital V out in volts, but that the ADC also adds in some error to represent the process of quantization. The amount of error you add depends on how far your input is away from a code transition. If your input falls right on a code transition, you're guaranteed to be plus or minus LSB over 2 away from a perfect linear relationship. But when your input falls halfway between code transitions, you introduce 0 error, because you're exactly on the linear relationship you are aiming for. If we take this error versus V-in plot and assume that our input spans several LSBs, and also that it's spectrally rich, meaning we don't just make the same pattern of codes over and over again, then we can model the error as a uniformly distributed random variable. That's just saying that we think it's equally likely for our input to land anywhere between 2 code transitions. The maximum and minimum values of the uniform distribution are plus or minus LSB over 2 to indicate the maximum and minimum values of error we could have. And the height of this distribution has to be 1 over LSB to ensure that our total probability is 1. The variance of this distribution is our quantization noise, and it has a value of LSB squared over 12. Great, we've got an expression. Digging into it a little bit, we can notice that it has units of voltage squared because LSB is a voltage. So that means quantization noise is a voltage noise variance, and we can add it to the voltage noise variance of other elements of our system. We'll soon see that increasing our gain reduces the effect of quantization noise, which is why we need amplifiers in our receivers. So in summary, quantization noise comes from the difference between the ADC transfer functions and a perfectly straight line, and that results in sort of an error versus V-in function, and eventually a uniform distribution of error if we have rich inputs. And the important takeaway is that the quantization noise is LSB squared over 12, and that it's a noise voltage variance.